Hello and good morning to all of you. I'm Dr. Chani Rallan from Circen Technologies, and thank you for joining us on this webinar. We at Circen Technologies have been hosting the series of webinar series as a platform to showcase the technologies which have been developed by the Water Division at ITRI. Our first session was a detailed, excellent presentation on the biological treatment solutions developed by the water team at ITRI Taiwan, and we covered the anaerobic sludge bed, aerobic process of bionet, and the sludge on our YouTube channel as well. This webinar, we'll be covering the advanced oxidation processes and Fenton technologies that the water division team at ITRI had developed. The webinar will be divided into two parts. The first part we'll be discussing and also full-scale application covering the advanced oxidation processes and how it can be applied as a pre-treatment step as well in biological treatments and how it improves the efficiency of the system. The end of each part, we'll be having a brief Q&A session as well with the panelists. So joining us as a speaker for the first session, for the first part of the session, and he joined ITRI in 2015 and is a researcher at the Water Division team at ITRI Taiwan. He's currently working on developing advanced membrane technology and biological treatment solutions for water treatment. Thank you, Dr. Yen, for joining us. We are very interested and excited to hear what you have to say. Over to you. Thank you.
Thank you.
Okay, can you see the slide?
Do you hear me?
Yes, we can see it. Yeah. You can make it full screen. Yeah.
Okay. Good morning, ladies and gentlemen. Thank you to everyone who joined this conference call. My name is Chia Yen. Today, I would like to talk about Fenton family technology. I hope this can help you to understand ITRI's wastewater treatment technology. First, I will talk some general information on advanced oxidation process. Chemical oxidation is to decompose organics to carbon dioxide and water with oxygen. And the most effective technology is LP. LP contains many technologies, including Fenton, and the Fenton-like, Fenton-like, and the combination of ozone, hydrogen peroxide, and the UV light, or hydrogen peroxide and metal ions, or UV light and semiconductors. But lead methods they have the same purpose. Lead is generating hydrogen radical for oxidation. The most commonly technology are Fenton and UV with ozone. Fenton method is a kind of LP which use hydrogen peroxide to generate hydrogen radical, using ferrous ions as catalyst. And the ferric hydroxide is final product. Hydrogen radical is one of the strong oxidants, and the oxidation potential of hydrogen radical is twice than chlorine. This photo is ferric hydroxide sludge. In general, the color of the sludge is dark brown. In 1894, Fenton is one first person who found this reaction, so called it Fenton method. The trouble with Fenton reaction is generating much ferric hydroxide oxide sludge. So required to pay a lot of money for separation and disposal. Based on sludge reduction, each developer a series Fenton technology. We call it Fenton family. The most used technology are Fenton 3 and Fenton 4. The Fared-Fenton is used to treat higher COD wastewater, suitable for over 1,000 milligrams per liter. And the FBR-Fenton is used to treat lower COD wastewater, suitable for below 1,000 milligrams per liter. The organic wastewater could be divided into refractory and non-refractory. In general, non-refractory wastewater goes to conventional biological treatment unit, and the refractory wastewater goes to Fared-Fenton unit. The effluent of Fared-Fenton can goes to treatment unit or biological treatment unit. Finally, FBR-Fenton can treat residual refractory COD to meet the effluent standard. This table is comparisons of the treatment for refractory high COD wastewater, including incineration, waste oxidation, supercritical fluid, UV light with ozone, and the conventional Fenton method and Fared-Fenton. The incineration and UV light with ozone and Fared-Fenton could be used to treat COD over 10,000 milligrams per liter. The capital cost of conventional Fenton method is the lowest, and the incineration is highest. But the operating cost of Fared-Fenton is the lowest, ranging between 2.3 and 4.4 US dollar per kilogram COD. Moreover, the advantage of Fared-Fenton is lower sludge generation. This table is comparison of treatment for refractory lower COD wastewater, including membrane separation, carbon absorption, chemical coagulation, ozone, and the conventional Fenton method, and the FBR-Fenton. The capital cost of conventional Fenton method is the lowest, but the operating cost of FBR-Fenton is only higher than chemical coagulation. The removal efficiency is only lower than membrane separation. In addition, sludge of FBR-Fenton is reduced 70% compared to Fenton method. Next, I would like to talk about Fared-Fenton method. In traditional Fenton reaction, ferrous iron will be oxidized to ferric iron. But the ferric iron can be reduced to ferrous iron by electrochemical reaction in Fared-Fenton. So the ferric iron will be reduced to ferrous iron at cathode. You can see here. Therefore, the ferrous iron can react with hydrogen peroxide continuously. It also could decrease the consumption of ion agent and the sludge volume over 70%. In this test, COD source was acetic acid, and its initial concentration was 10,000 milligram per liter. At 6-hour reaction time, the COD of Fenton process only decreased to 6,000 milligram per liter, but the COD of Fared-Fenton process came down to 1,000 milligram per liter. Overall speaking, removal efficiency of Fared-Fenton is higher than traditional Fenton method. In addition, Fared-Fenton is a kind of electrochemical reaction. So its temperature will go to around 60 degrees C, less higher than conventional Fenton reaction. In this test, Fared-Fenton was applied to treat petrochemical wastewater. Hexamine is a kind of refractory organics. That's not easy to treat by traditional biological treatment. Please see this chart, which the COD could be decreased from 17,000 milligram per liter to below 500 milligram per liter. But the operating is uneconomical when reaction time is over 4 hours, because you have to waste too much hydrogen peroxide for removal lower COD. This curve means too much residual oxygen in wastewater from excess hydrogen peroxide agent. This case is an application of Fared-Fenton for treating flushing wastewater from a semiconductor plant. This flushing wastewater contained IPA, acetone, MEA, and phenol. The COD is 11,000 milligram per liter and flow rate around 1 cmD. This batch test had 4 steps. First one, the wastewater goes through bulk tank and get into reaction tank. At the same time, the ferric ion will reduce to ferrous ion in electrolytic tank, and the ferrous ion can react with hydrogen peroxide continuously by keeping water cycle with reaction tank. Next step is sedimentation and the pH adjustment. After purifier process, the treated wastewater goes to discharge, and the ion sludge will be dissolved in pH 2 for next operation. This photo is electrolytic tank inside. We can load it. Okay. Here is an anode rocks, and here is cathode screen. This picture is electrolytic tank and a purifier. This is operation panel. This one is a reaction tank, and here is electrolytic tank, and this is clarifier. We can see pH, DO, ORP, and some important information on the panel. This table shows the data from the test runs. The COD of influent are ranged between 10,000 to 25,000 milligram per liter. And the removal efficiency of COD are all over 95% in Fared-Fenton process. After sedimentation process, the inference is very clear, and the COD are all below 1,000 milligram per liter. Next, I would like to introduce FBR-Fenton method. FBR-Fenton is a kind of Fenton method based on fluid light condition. When a Fenton reaction is carried out in tower-like reactor, the iron oxide will crystallize on the carrier to achieve the sludge reduction. It could decrease over 60% sludge compared to traditional Fenton method. FBR-Fenton could be used for treating refractory wastewater, deep colored wastewater, or the Fenton containing wastewater. The FBR-Fenton is similar to conventional Fenton method. They also have a homogeneous reaction for produced hydrogen radical, but the carrier has heterogeneous reaction of iron oxide to produce hydrogen radicals. So it can save the dosage of ferrous iron and reduce the cost of sludge treatment and disposal. Please see this photo. The color of the carrier will slowly change to dark black, which is related to thickness of iron oxide layer. This case is for treating ABS resin wastewater. The COD of the raw water is 3,000 milligram per liter, and the COD will decrease to below 200 milligram per liter after biological treatment. In FBR-Fenton unit, the COD of influence are ranging between 100 to 150 milligram per liter. Finally, the COD and the SS of influence are below 60 milligram per liter and 20 milligram per liter, respectively. This one is tower-like FBR-Fenton reactor. And the upper right is top view of reactor. Please see lower right. These are water distributors for fluid stabilization. Here are other photos of equipment, including dosing pipe, feed pump, dosing pump, recycle water pump. Finally, this table is ITRI's family. application for your information. But the information is in recent years has not been updated, so this is relatively poor information. This is the end of my presentation. Thank you.
Thank you. Thank you, Dr. Yen, for that detailed presentation on the We have one question from Mr. Suresh, who would like to know, is your technology similar to electrocoagulation?
I think it's slightly different. Although they are all using about.
Sorry, Anne, can you speak a bit louder, please? Because
sorry, let me brief mention about that. The electrocoagulation is different to the electro oxidation, which we call it like a Fenton process. And the Fenton process is to generate the oil radicals in the water solution by the electron transfer. Yeah, and also they use some like the Fenton reagents like a ferrous and hydrogen peroxide. And the electrocoagulation is by using some special material of the electrodes like the aluminum and ferrous, and to produce this kind of ion in the solution and have the coagulation phenomena occurs. So it's different mechanisms about the organic decomposition process.
the attendees on this part of the session, I don't think we have at this moment. Oh, we've got one more from Mr. Mohsin Anwar, who would like to know, why is AOP is pH dependent, and how can we work with AOP on different types of pH?
Can you speak again?
Why AOP is pH dependent, and how can we work with AOP on every pH?
Normally, we will do some preliminary study, because for the strong oxidant like oil radicals, which is more suitable in acidic condition, especially in the Fenton process. So normally we will do the preliminary study about different kind of situation for the organic decompositions. Yeah.
What kind of electrodes are suitable for Fenton process?
What?
What kind of electrodes are suitable for Fenton process?
Okay, for this kind of issue, normally we will use like the dissoluble anode material, which is coating kind of like a metal oxides in titanium substrates. And these are the electro material we commonly use, and which can stand for the long-term extreme conditions like the strong acidic and the high oxidation conditions.
Okay, thank you. Thank you, Dr. Zhuang, and thank you, Dr. Yen. That was an excellent first half of the session. So we could move on to the second part of the session. We have Dr. Chun Chi Lee, who is a researcher at the Water Division team at ITRI Taiwan. He received his PhD from the National Tsinghua University, and his research was focused on the utilization of advanced oxidation processes in treating semiconductor wastewater and variable AOP systems tested as pre-treatment system for biological treatments. This session, and hi, over to you, please.
Thank you. Okay.
Okay, so we can start to share the slide, okay?
Hello, this is Chun Chi Lee. I come from ITRI Lab, and today is my presentation topic to share to all of you is the advanced oxidation process, similar to that Dr. Yen had talked before. And this process was applied as a pre-treatment process for the enhancement of the biological treatment efficiency. And just like the topics, like the COD treatment method will be related into divided into two parts. One is the biotreatment, and then the other one is the physical method. And using the biotreatment, we got many kind of advantages, like the footprint. The cost is lower because using the anoxic conditions, you can treat loaded to 8 to 10 kilogram per tons per day. Using oxy conditions, you can maybe to 2 or 3 loading. And the organic carbons will transfer into the methane, carbon dioxide, and the biomass. And for the physical method, we use the AOP, just like Dr. Yen had mentioned about, is the Fenton reactions. We use the hydrogen peroxide reacted with the ferrous ions, and then produce the hydroxyl radicals and to attack the carbon links to the carbon dioxide. And then the other one is use the UV oxidation. Use the UV light to react with the water and produce the hydroxyl radical. But it's more important is the waters. Your target compound should be transparencies. Otherwise, the UV will be inhibited. And then the final one is the oxidation. Use the ozone or chemicals like sulfate. And here you can see their comparisons between this method. And you can find out a lot using the biological method. We can get low cost effect, low cost and high effect efficiency. But it's hard to control because of if the compound is non-biodegradable or is bioinhibited, then your biological system cannot treat this kind of CODs. However, using AOP, we don't need to face these kind of problems. Everything like high concentrations or hard degraded CODs can be decomposed. Just use the chemicals reactions. But there's more disadvantages than the chemical residues. Use Fenton, no matter which kind of Fenton, Fenton 1, Fenton 2, Fenton 3, Fenton 4, you will reach the ferrous ion or ferric ions residues in your systems. That can affect the water if you need to reclaim these waters to the reclaim water systems. So if we can combine these two kinds of the systems, then we can use the system to do the reclaimed waters. Then we can now the biological treatment. If we apply in the reclaimed water, the reclaimed water, after reclaimed water from the municipal water or industrial, it is after the secondary treatment. We can see from the slide this is the first water come from the factory or for a pre-treatment process, and primary and secondary. This is a biological treatment, and released. The COD content was low because content was low, around 30 to 80 ppm, but the release of the COD is non-biodegradable. It is produced non-biodegradable. And if you want to use a biological treatment to treat the bioinhibitors, like the peptides, herbicides, antibiotic or pharmaceutical wastewaters, then this kind of like a penicillin or methylene terpene is under the low concentration is inhibited for the biological treatment. So in this case, the biological system has so many advantages that we have the cost effect is cheap and then can high throughput to treat the CODs. But to face this kind of situations, we cannot use the biological treatment to do it. So here we introduce the ozones into the system as a pre-treatment, and then now I introduce some properties of the ozones. In 1840s, ozone was produced artificially in France, and after 20 years later, ozone was first applied in air sterilized in Paris, and then later in 50 years later, ozone was applied first in water purification in New York. And the most important thing is the half-life of the ozone. In the in under 25 degrees Celsius in air, the half-life of the ozone is around 20 to 100 hours. Most important is around normal conditions in waters, the half-life of the ozone is around 3 hours. Especially if some impurity like the COD or the impurity of the ions inside, the half-life of the ozone can be decreased into 30 to 50 minutes. So that's the reasons, and the most important is if you use ozone as the pre-treatment systems, it won't affect the secondary to the biological systems. So if you use ozone as an oxidant, and first we call initiation step, the ozone will react with the water to produce hydroxyl radicals. More important is under the best conditions, it will produce more hydroxyl radicals. And then the ozone will react with the hydroxyl radical to propagations of the hydroxyl radicals, and then finally terminated. So in these steps, we can find out that the ozone treatment can conduct on the neutral pH and the higher pH values, except the acidity pH values, so it can work. So here's a summary of our reactions. Here we can divide into two parts. One is the direct reactions and the secondary reactions. And the direct reaction we call it as ozonations is ozone as oxidant to oxidize. And the secondary reaction is ozone to react with the water and produce the hydroxyl radicals. And the pH value should be higher than 7 on the FB in the best conditions, and then it work. And the most important is the byproducts. Using the ozonation, the byproducts various. You can divide it, the bondings of the compounds. But if you use the hydroxyl radicals, it can mineralize the CODs into CO2, carbon dioxide. So if you use the ozone without the high dosage, and we can transfer the COD organic compound inside to the small part, or to detoxify the CODs. And we use ozone in reclaimed water systems. It's very important is that the resource of the reclaimed waters, the water taken from the treated municipal or industrial effluent. And after that, you can find out the figures here. You can find out that there's the analysis of the effluent of the municipal and industrial effluent. The TOC analyze the molecular weight of the TOC inside. You can find out that this one is from the municipal and industrial effluent. The TOC contain high content of the non-biodegradable TOC. However, compared to the tap waters, they are completely low. So if we use the recycling use of the industrial effluent, we will face that we use the major purified technology is EDRO. This kind of the huge molecules will cause a serious membrane fallings or biofallings. So if you use the reclaimed water system, we use the normally we don't use we use the MF to filter it, and then we contact to UF and to our system to purify. If we don't have the pre-treatment, then UF or our system will easily fall by this kind of the big compounds of the CODs. So we will easily to use the biosystem in front of as a pre-treatment to treat this kind of the CODs. But the COD released from the secondary treatment, the CODs cannot be easily decomposed by the biological system. So in here, we are first introduced using the ozone as a pre-treatment systems to digest or to decompose this kind of the macro molecules into small molecules and enhance the biodegradations. So in the ozone applications, traditionally it was set up in front of our system to prevent the growth of microorganisms that were frequently used, or use the final treatment process, not only for the sterilization, sometimes to prevent the accidental release of the high concentration of COD into the COD. So from the quantification is that the ozone dosage to COD for the mineralization COD is around 2 to 4 times. It indicates that the 4 grams of the ozone was needed to mineralize 1 gram of COD. It costs a huge amount of the ozone. But if we think in other angles, if we combine ozone as a biological system, we can use a small dosage of ozone and then just to break the boundaries of the CODs, and they can enhance the biological process, and they can best the same behaviors. So we can, as a pre-treatment process in front of the biological system, and then to enhance the biological treatment efficiency. It increases the lower ozone dosage was applied just to break part of the chemical boundaries. From experiments, normally it's around 0.5 to 0.5 ozone loading to COD was amended, which means that ozone loading was 40 times lower than the traditional ones if we combine the ozone system to the biological systems compared to the simple ozonations. Here's the pilot study we set up in Kaohsiung City and in the one industrial park as the resource. So traditionally we'll use the MMF as the first stage, and then to the UF system, and then to the RO or EDR system for the locations. So in this case, we'll use the AOP as the MMF, and then AOP systems, we use the ozone as a pre-treatment system, and then combine to the biological system to enhance the biological behaviors to digest the CODs. And here is the organic content species analysis in this science park. We can find out that the raw water the COD can be divided into 3 parts. One is the low molecular weight and the humic acid-like, and the most important is the molecules we call biopolymers, which were thought will get a serious falling on the membranes. So the raw water here is around a big value is around 50 intensity. And after simple to the bionic systems, the biopolymers also remaining because the biological system cannot decompose or lose biopolymers. And then to the ozone systems, there nothing happens because the dosage of ozone is lower, and they can just change the species inside the macromolecules to small molecules, but will not change the COD values. However, if we combine the ozone to the bionic system with the loading from 0 to 1.2 values or ozone value to the COD values, we can find around 0.5 loadings. We can change the BODs around 40% of the COD to BOD. It means that the biopolymer can be decomposed after ozone treatment, and it can be digested by the biological systems, which means that the biopolymer will be decreased. And you can see the green light here. And it's more important is that with the lower content of the biopolymers, we can use the UF membrane to test it. We can use the recurrent water UF membrane for a test, or we call it American test to using the water to penetrate membrane. We can find out with the treated water amount, the flux will decrease without the treatment, and the balance system will decrease sharply, and with the ozone also sharply. But with the ozone combined with the biological systems, the flux will decrease slowly. And we are applying in the real pilot scales is the 200 cubic meter per day. The pilot scales we are applied it. We can find out without the treatment, only the biological systems, the flux will decrease after 15 tons of the use. The flux will decrease sharply. However, if we combine with the ozone systems with the ozone in front of bonnet of the biological system, or in the after the biological system treatment, the flux of the membranes can be maintained, which means that the combination of the ozone can pre-treat the CODs into the biodegradable and enhance the biological treatment, and it can enhance the UF the use life of the UF and the more in the back to our system or the EDR systems, which can decrease the reclaimed water cost. And here we use into the antibiotic or herbicide or pesticides of the about inhibitors. Yeah, this slide just want to tell you that this is a very complicated process, because this kind of the compound, even under the low concentration, is also inhibitor to the biological systems. And after ozone treatment to break down to break the balance and it come to the small molecules, sometimes also toxic to the biological system. So we need to test for every steps. And just want to show you that we can use this kind of, from reference, we can use this kind of the testing to know that which ALP steps should be located in which part, and in which cases you can use which kind of the ALP system in which part. And here's a search we search from the references is along to the herbicides is a TBT or CT, like the structure like we have shown here, and it is the beta tone herbicides used for the poster images application on corns, and the loading of the herbicide ozone to the herbicide molar ratios 0 to 2, and with the increase of the ozone loadings to 0.5 to 0.75 to 0.75, the decrease of the SCT will transferring to the other byproduct compounds, and then decrease slowly with the inhibitions around 40%. So it means that we decrease this kind of herbicide, but the residue still has some inhibitions, but we did decrease the inhibition percent. And the most important part is the ozonation. We should put the ozone into the water, and dissolve the ozone is very dependent on the temperatures. So here we use the normal bubbles, but if we can transfer into the microfine bubbles, that increase the specific surface area. Normally, if we change from the normal bubble to some micron sized, the reaction surface will increase the 10,000 times higher. However, moreover, the density change, the length of stay time in water increased because the micro bubble, fine bubble density is higher, so it will precipitate on the bottom of the waters, so enlarge the reaction time. So the overall the contact time transferring from the normal bubble to the microfine bubbles can increase around 200,000 times higher than the normal bubbles. Now you can use in the situation with the a little bit higher temperatures situations. So here goes the conclusion that in the use the ozone combined with the biological systems in the reclaimed waters, ozone can be applied as the pretreatment of the biosystem to break the reticulate organic matters. Then without a serious pH control, pH not except the acidity, pH higher than 5, then you can go this kind of the phenomena. And then the ozone dosage control at 0.5 to 0.5 times of the steady content is case by case, but normally lower than 1 time, lower than 1 to 1. And the result shows that ozone as the pretreatment can prevent the falling on the membrane systems. And as for the biological inhibitors, it is serious because it should be case by case. It depends on which kind of the structure, which kind of compound we use that we are facing. We can, in a different process, using ozone as a tool to detoxification and enhance the more biodegradabilities. And normally, ozone loading was dependent on the targets, normally around 0.5 to 2. And the ozone microbubbles we are applied to increase the ozone content times, which was it will spend a little bit of the electricity, but they can enhance the great dissolved ozone in waters. So here we are presenting one kind of interesting combination of the ozone as the pretreatment of the biological system, and the results can give the support that with the ozone as a pretreatment can enhance the biological treatment. So this is today's presentations, and thanks for your attention.
Thank you. Thank you, Dr. Lee. I think that was quite interesting to see how we could use the ozone system as a pre-treatment method. So maybe now at this point, we have any questions from any of the participants. If you could just put it in the Q&A or the chat box if you'd like to ask Dr. Lee any questions pertaining to this type of technology. I don't think we have any questions as yet. I have actually a question. Dr. Lee, this is quite an interesting thing. Is this being applied currently only at pilot scale, or are there full-scale applications of using this pre-treatment step?
We are just in the beginning. We have a lab scale tester, and the one is we have shown the slide is in pilot scale. It's around 200 cubic meter per day, the pilot scales, and we test this kind of the phenomena. Yeah, and we do the great result to prove that the ozone can be as a pre-treatment system that we have never seen in the pilot scales. Yeah, but we have only yes.
Okay, that's quite interesting. And what kind of industries do you see this being applied in? What kind of effluent treatment plants?
What kind of?
Effluent treatment plants, like what kind of industries? What specific?
In our pilot scale test, we are using as declined water systems. We use the influence of the industrial or municipal waters that is treated after the plant, treated waters, but it contains some reticulate COD that will float on the membrane, but cannot be removed by the biological system again. So we use the ozone in front of the biological system to digest the COD into the biodegradable. And we are trying to fast into the herbicide or the pharmaceutical industries. But it is really hard because it should be know exactly what kind of the compound we used. And after the ALP treatment, it may be the toxin may be not so significant, but we are trying to do how to enhance this kind of the bioinhibitors to the biodegradables. Use the ozone as a pre-treatment, but it should be tested case by case.
Okay. And we have a question from Mr. Marimutu who would like to know, what about waste generation in the use of ozone?
What
about waste generation when you use ozone?
Waste generation? No, because if we use ALP, we can select many kinds of the ALP system. Like in the previous, you can use the Fenton reaction, but will produce the ferric iron minerals. But if we use the ozone, and then we have present in the slide, ozone will be decomposed in waters. The half-life around 30 to 50 minutes, and after that, the ozone will be decomposed into oxygen and waters. So and especially we are combined to the biological system, so we are choosing the technique that it will without any chemical resistant insights. So that's why we are choosing the ozone as a pre-treatment process.
Okay, and we've got another question. You mentioned about recalcitrants. Does this apply to emerging contaminants too, like pharma and personal care products? You mentioned about emerging contaminants. You mentioned about using ozone treatment for emerging contaminants. Does it apply?
Yeah.
Can you use it in pharma treatment and personal care?
Yeah. We use ozone as the final stages to prevent the emerging release of the COD. That you use the high concentration of the ozone to treat it. That we have frequently seen in Taiwan using the ozone or the Fenton reaction final steps to treat this kind of suddenly release of the COD.
Okay, we have another question from Dr. Ganesan. It's quite a thing which is I'm sure on all our minds. Is ozone treatment an economical treatment?
Only ozone treatment is not economical treatment because it costs a lot of money. But it's one I just want to link the ozone system to the biological system. The ozone is only to treated part of the ozone, so it's around compared to the traditional to the mineralization is around 40 times lower compared to the normal ozonation process. Just we combine the ozone to the biological system to decrease, to have the advantages of the low cost of the biological system, but can also have the ozone process to enhance the biological treatment. So we combine it. We combine these two processes, then the price will be lower than the normal ozone use.
Okay, so if basically, so if we invest in this, our overall comes down. So we have an overall savings in the overall OPEX essentially comes down for the plant. Okay.
Especially for this kind of the hard to non-biodegradable CODs, but it will affect your systems. If later maybe our membranes, they will fall in our membranes, and they will need to flux or to rewash our membranes. If you pay a little bit of the ozone inside, it can prevent a serious problem happen later. So that's why we are trying to push this kind of technique and combine these two together.
That's very interesting to know. So by adopting this, we are having lowering the chances of RO fouling as well, and all our membranes downstream. And I would imagine even the UF membranes as well. We have a question from Dr. Emmanuel, who would like to know, can the microbubble system be added to existing ozone units?
It can generate easily with a simple equipment, but it is it's not hard method. We can use a simple equipment to produce the microbubbles. Yeah.
Okay.
Yeah. I did not show it very detailed because it is we can purchase the product that you can purchase from. You can purchase it. It's a machine that can generate the bubbles. Then you can just link to the ozone gas. Then you can produce the ozone microbubble. Yeah.
Oh, so you can do it.
Yeah.
Okay. And we've got I think and then how much sludge is produced during the process?
How much
sludge? There's no sludge in this. I think it's probably
sludge produced only for the biological treatment. Only for the biological treatment, we are trying to treat the carbon mass, the COD into the CO2, so the sludge will be less. Except there's the yield of the biological system is 0.4. 1 gram of the COD will produce the 0.2 to 0.4 of the CODs if we use an acid conditions.
Okay, we have a question. We have a question from Ms. Saranya, who'd like to know if there are residual radicals of ozone, won't it affect the subsequent biological processes?
Yeah, if you add the high dosage of the ozone, but we don't need it because the ozone dosage should be calculated, especially for the calculated to the CODs. We are mentioning about 0.2 to 0.1 to 0.5 loading of the compared to the COD inside, and we have discussed before that the ozone in the water, especially we have some COD or impurity inside, the half-life around 15 to 30 minutes, so it won't affect. It will decompose during the transfer from the ozone part to the biological part. Inside the pipings, they will be decomposed of the ozone. So it's really to infect the biological systems, but it will happen, but it can be controlled.
Okay. Wow, that's very interesting. And so this is quite a new technology then, and it's quite new. It's very new technology which you are working on, and I mean it's still only in pilot. 200 CMD plant you mentioned. Okay, good. So where I think piqued most of our interest as well, especially mine. So thank you, Dr. Lee. I think that was an excellent session. Thank you for answering all of our questions. I think we have some more questions we will try and answer by email. Thank you, everyone, for joining us for this webinar. Our next webinar will be on EDR, the electrodialysis reversal process, and fluidized bed crystallization, which we will have in a couple of weeks, the details of which we will post on our LinkedIn page and also share with you by email. The EDR, I'm sure, I think most of you know that we have been facilitating pilot plant trials of the EDR system at Rani Tech CETP, where we've been treating the RO reject that's produced there. So as I'm sure most of you know, it is the harshest tannery effluent that is produced. So we'll be showcasing these results as well in our next showcase webinar. If you would like to interested in these technologies, would like to know more, please do reach out to us at Circen Technologies. We have a technical collaboration with ITRI Taiwan, and we're promoting the technologies in India. So if you'd like to know more how you can implement this at your treatment site, please reach out to us, and we could schedule a call, a video consultation, even if required, and we could see how we could proceed with your requirement. Thank you, everyone. This webinar will be uploaded on our YouTube channel. Thank you again to our speakers, Dr. Yen, Dr. Lee. Thank you. Excellent sessions as always. Thank you, Dr. Zhuang, for helping out as well. Thank you, everyone. Thank you. Thank you. Bye-bye. Bye-bye, everybody. Thank you. See you all soon. Bye.